Hey friends, it's Ben again. So we're going to try to do some stuff with related rates here in the differential calculus class. Sorry, I'm trying to make sure my little plug-in is plugged in. So, but related rates is this this setup where you get, let's be honest, this is the word problem section. If you hate word problems, then this probably is going to feel a little bit miserable. The main thing that you have to do with these is to read the problem and from the problem divine what, I guess, what's it asking, right? But what equation do I need to write down? If it says volume, you say volume of a what? You look up, which thing is out there for you to use, and you write that down. And then it'll say a rate of change of this, usually with respect to time, okay? But it might say a rate of change with respect to one thing or another. So as you're doing these, you're going to have to take derivatives, but usually the derivative is not going to be super direct. It's going to be something like a rate of change of distance with respect to time. And you've got this equation that has distance not solved for, but just appearing in it. So, all that implicit differentiation stuff that we did, it's that. But then with the chain rule and then with the product rule. So it's something, okay? But it's stuff that we can totally do. We just have to have the patience to do it and to look up any formulas that we need. All right. So I have prepared problems ahead of time. I did not work them out, and that means that they may take a while to get to work out. I did not work them out, but I did stop and try to draw the pictures so you didn't have to watch me struggling with my artwork. Okay. All right, so let's see whether we can do some of these, and we're just going to launch right into it. And I'm going to try to give you suggestions along the way of how to think these things through. So if you're watching the video with the sound turned off, oh, good luck. I'm trying to give you motivation here. And so with each thing we do. All right, so this setup here, we have an 18-foot ladder and it's up against a vertical wall. Now, it may not be entirely clear here, but if we're talking about walls for houses or anything else, we're always assuming that they meet the ground at a right angle. So that's going to figure into this problem here, and it'll figure into some other problems later. So make sure you catch that. So we got an 18-foot ladder resting against the vertical wall, and somebody's grabbing the base of the ladder, and they're going to move the base of the ladder away from the wall at 5 feet per second, okay? And the top is they're just letting it scrape down against the wall, right? And so it wants to know when the foot of the ladder is 10 feet from the wall, how fast is the top of the ladder falling, okay? And then there's the other question that may seem weird, but I'll show you why it's not that weird. When does the acceleration for it hit 32 feet per second squared? Okay. All right. So taking a look here at what we're doing, this up here is a right triangle. And that right triangle, I've gone ahead and labeled X and Y to be the two sides of it, and I know the hypotenuse. And I know this guy named Pythagoras, and he told me that right triangles always have this particular equation to be true for them, okay? Now, what you got to realize with this, with the ladder sliding along there, is that X and Y are both changing. They're not constants. But the length of the ladder is a constant. Hopefully that's not like blowing your mind or anything, but yeah. So now we're going to differentiate this implicitly with respect to time. So on the left-hand side, you have to think about the derivative of x squared, which of course would be just 2x, but then the x is changing with respect to time. Same thing happens with the y. Okay. And then that 18 squared on the other side is just a constant. I think 18 squared is like 324. Let me go check to make sure. Yeah, 324. But because it's a constant, when we differentiate, we end up with a 0. Okay. And now what we're going to do on this problem, once we get it to there, we have to identify that we are looking for dy dt. dy dt is how fast the top of the ladder is falling. And all of the other information is given to us, x and dx dt. Y is not actually given to us. I'm sorry, I lied to you about that. But it's something we can figure out by looking back to this equation. So if you plug in that you want the x to be, what was it, the x to be 10, then 10 squared plus y squared equals 18 squared. Y squared is 224. So y is equal to, wow, 224 is divisible by 4, 4 again. So it is 4 square roots of 14. Okay. I always advise people leave things in exact form until you get to the end of the problem, and then you can approximate. Okay. That way you don't lose any digits due to propagation of error. But so what we've got in this problem is 2 times 10 times 5. Now stop and look at that real quick. The 5 is going to be a positive 5 because we're moving the bottom of the ladder away from the house. So we're increasing our value for x. But then plus 2 times 4 root 14 dy dx equals 0. And I wrote dy dx, and I did not mean that, dy dt equals 0. So then all we've got left to do here really is the arithmetic. Dy dt for this is going to be negative, let's see, 20 times 5, negative 100 over 8 square roots of 14. And if you need an approximation for that, because we always seem to, 100 divided by 8 square root of 14, I'm getting about 3.341, and the units would be feet per second. Okay. And if you're talking about some painters who want to know how fast their ladder's dropping and stuff, you probably don't really care about that many digits. Probably saying 3 feet per second would be good enough, right? But that is the first piece of the problem. We're figuring out how fast the ladder is dropping at a certain time, okay? So I'm going to take that piece that we did there, and I'm going to push it over here, because now we need to do a little something else with it. And the something else is going to come from this part up here. Instead of solving when we are a certain distance from the wall, we're going to try to actually solve for dy dt. The reason that we need to solve for dy dt is going to have to do with the fact that we want to find the second derivative. We want to know acceleration. Okay. And this may get a little bit icky, so bear with me. So if you go ahead and plug in the things that we do know from that, then you know that the rate that the bottom of the ladder is moving is 5 feet per second. And so we end up with a 10x here plus 2y dy dt equaling 0. And that says that your dy dt is going to need to be equal to negative 10x divided by the 2y. I think I'll put it as negative 5 times x over y. Okay. Now, keeping in mind that we can deal with dx dt and dy dt and stuff like that, we're going to now find the second derivative with respect to time. You can leave the minus 5 hanging out there, but we're going to have to actually use the quotient rule, which I have to be honest is always hard for me to remember what order to do things in. So the derivative of the top goes first, leave the bottom alone, minus the leave the top alone and take the derivative of the bottom. Okay. And then here on the bottom, we will have the bottom being squared. All right, that's pretty nasty looking, but some of it we already know. The dx dt we said was 5, so we have a 5y minus x times dy dt we solved for a minute ago and have it as minus 5x over y, all that divided by the y squared. We're going to try to simplify that as best we can. All right. Do you all see that there's a factor of 5 coming across the entire top there? So that we can say minus 25. And then we would have a y, let's see, minus a negative, and the x squared divided by y. All that divided by this y squared. All right, that is too much stuff on one side. I am going to add a page here. And on the new page, I'll just paste where we were with this. And so now to simplify a little further, I'm going to multiply the top and the bottom by y. The reason I'm doing that is to get rid of the fraction inside of the fraction. So, oh, shoot, did I lose something there? No, oh, that's okay. All right, so I end up with minus 25 y squared plus x squared, all divided by my y cubed. All right. Now that y squared plus x squared, I am fortunate here that I can simplify that a little bit further. Y squared plus x squared, remember, was 18 squared. So over y cubed. Okay. And so 324 times 25. So negative 8100 divided by y cubed. All right. So you may be thinking, why are we doing this? Well, we want to know when the acceleration actually hits 32 feet per second squared. And it's 32 feet per second squared down, right? The reason for that is to actually look at how something models reality. If you actually watch a ladder slide down a wall like this, at some point, the ladder actually comes out from the wall. And you'll have things just fall to the ground. The reason that it does that is it can't accelerate any faster than gravity. So at this point, we're actually having the ladder be accelerating at the same rate as gravity. And that means that you can go ahead and solve for this and have 8100 over 32. And I'm going to have to grab a calculator and just get a good approximation there. And so 8100 divided by 32 to the power of 1/3 for a cube root. And the y value that I'm getting is 6.326 blah, blah, yada, yada, yada. Okay. So what that says is that when the top of the ladder is 6 feet from the ground, you actually end up having it come away from the ground. Now, you could also, with that, solve for the x instead, just by substituting differently. And then I'll have to, real quick here, say I'm going to square that and do something with a 324 and take a square root. That was second square root. Wow. Okay. Okay. Second square root. It is embarrassing how much calculator effort that took me. 16.852. Hey, oh, thanks. So 16.852 feet. So when you get an 18-foot ladder, almost 17 feet away from the wall, that's the time when it's going to start not sliding down the wall apart anymore. So the weird bit about this is if that didn't happen, if you could just have your top of your ladder continue increasing indefinitely, then it would have to go faster than the speed of light. And it can't do that. So, yeah. All right. Anyway, though, that is the point at which the ladder separates from the wall. All right, let's hit another one here. So it's an estimate that the number of housing starts per year in a T, keep in mind that this is in millions of housing starts, is related to the interest rate in percentages. Now it's saying percentages means it's not a decimal, okay? By 9n squared plus r equals 36. So we're going to figure out the rate of change of the number of housing starts if the interest rate is 4%. And it's increasing at 0.1% per year. So first off, let's figure out that if you took 9n squared plus the 4% equaling 36, then that says that your n squared would have to be 32 over 9, which says the n, we're only going to consider positive ones. We're not going to have housing demolishing counting. So square root 32 divided by 9 is 1.8856. Okay, so I'm going to rewrite that last bit as a 6, right? And keep in mind, this is in millions of housing starts per year. So we're talking about nearly 2 million housing starts. All right. Then what is the rate of change of the number of housing starts? So we're going to think about 9n squared plus r is equal to 36 and differentiate implicitly so that you end up with 9 times 2n dn dt. I wrote my t wrong. dt plus dr dt is equal to not 36, because you have to take the derivative of a constant, so we get a 0 there. Okay, so we have 18 times this 1.886 million and stuff dn dt plus the dr dt, it said was increasing at 0.1% per year, and we want to set this equal to 0 and solve. So that means that your rate of change here needs to be equal to negative 0.1 divided by the 18 times 1.886. And then, yeah, then negative 0.1 divide 18 times, oh, and I hit it on there on the calculator just a minute ago. So that answer, and what I end up with is negative 0.002946. And there's more digits to it, but remembering that this is all an approximation anyway, that says that we are expecting a decrease of, and this is your percentage of or your decimal of a million. So if you go ahead and multiply that by a million, you have 2,946 housing starts. Okay. So we expect that much of a decrease in the number of new houses being built when the interest rate is increased by 0.1%. Does that make sense? Yeah, when the interest rates go up, that means it's more expensive to start building a house. It's also more expensive to start buying a house and stuff. So you'll have fewer houses started out. So always good to do a sanity check on these things. All right. Here's another one. We're looking at a baseball diamond, and I have to give you the piece of information in case you're even more of a nerd than me and you don't realize that a baseball diamond is actually a square, and the sides of the baseball diamond are 90 feet on the side. Okay. So a batter hits a line drive. Line drive means that it goes right up the middle. So those are super duper dangerous to pitchers. If they get hit in the head with one of those, it can end their career. So anyway, though, the baseball diamond is a square with 90 foot sides. A batter hits a line drive, and the line drive is going at 80 feet per second. And then he runs towards first base at 30 feet per second. And then we're going to ask a question about how fast the distance between him and the ball is changing. So one thing with respect to this is that it is kind of sort of set up, assuming he drops the bat and is running immediately when the ball leaves the bat. But play along a little bit with that portion of it. So what we need to realize here is that we can talk about a triangle, and that triangle, the sides of it are going to have a relationship that we refer to as the law of cosines. If you didn't have a trig class and don't know that one, then you have to look it up to know that it's a thing. So fortunately, the angle that we're talking about in this triangle is a 45-degree angle. It doesn't change. But these distances here all change, right? So we're going to be thinking about the rate of change with respect to time. And so we're going to take the law of cosines there, the a squared equals b squared plus c squared minus 2bc, and we're going to put in the cosine of 45 degrees, which is the square root of 2 over 2. So that means you can do a little bit of cancellation there and simplify it right off the bat. Haha, bat, right? Okay, I should shut up. But now we're going to differentiate implicitly like before. And so you end up with 2a times dA dt. Remember, every one of those quantities is changing, is equal to 2b times dB dt plus 2c times dC dt minus the square root of 2. And now we've got b and c, so we have to use a product rule. we'll have dB dt, leave C alone, plus B left alone times dC dt, right? So we fill in everything that we know. We knew what the cosine of 45 degrees was, and we filled that in right away. If we hadn't done that yet, we would have to do it now. So what we'll have to spot from the reading is that we actually have a value for B. He's run 60 feet. And how fast was he running? dB dt equals 30 feet per second, okay? Um, just to mention in passing, I looked it up to see whether that number about 30 feet per second is realistic. That's like world record running speed. So that's a little crazy. Then for the C here, we can figure that out as well. If he dropped the bat and was running immediately, that means that he had to run 2 seconds at that speed. So the ball has been flying out there for 2 seconds at 80 feet per second. So the C is 160. And then we said that dC dt, the speed the ball was moving, was 80 feet per second. So let's fill in everything that we know there and just see. 2 times A dA dt, we don't know those yet. 2 times the B was 60, the dB dt was 30, plus 2 times the C, we said was 160, and the dC dt was 80, minus square root of 2 times, dB dt was 30, and the C was 160, and plus the B was 60, and the dC dt was 80, okay? So you can figure out your dA dt here. I am going to go to a calculator for this because those numbers are just too much for me. So bear with me just a second here. Okay, so, oh God, 29200 minus the square root of 2 times, let's see, 9600 square root of 2. All this divided by the 2a. Now I guess I can divide by 2. So this may feel a little bit discouraging here, but have 14600 minus 4800 square root of 2, all divided by a. The only thing we're missing is the a, and we actually have the numbers to do that, right? So if you look back over here, we can actually plug in and figure out the a. So a squared equals, the b squared is 60 squared, the c squared is 160 squared, and minus a square root of 2 times the 60 and the 160. So I'm going to take a square root after I put all that stuff together, but it shouldn't be too terribly bad. Oops. Except you got to make sure not to hit minus when you mean plus. Minus 60 times 160 times square root. Oh, I forgot to do my square root. I'm getting 112.126 stuff. for my A value. And so I am going to go ahead and take my 14600 minus 4800 square root of 2, close, divide it by that A, and I'm ending up with 69.669 blah, blah, blah feet per second. Now, realistically, you have no need to get it that exact. You can just say 70 feet per second, right? But we've got the numbers, so I went ahead and left it in there. Okay. So we're taking another look here. We've got two resistors that are connected in parallel. All right. I don't have really a diagram for this, so, but it is super handy on this to think about it like this. Okay, so you've got all those powers going on there. And then when you differentiate, because you're using a power rule and a chain rule, it's a little bit less of a pain, a little bit. And so out to the side here, I'm going to later need to figure out what that R value is. And so I'm going to write down R inverse equals 75 inverse plus 120 inverse. And so the R that I'm going to have to plug in later on is going to be, let's see, 75 inverse plus 120 inverse. And then I have to put the right number in. End up with 46.154 ohms. Okay. Now, I don't know how exact those things, it's realistic to actually talk about them. So I'm going to go ahead and leave it like that. But if you know better, then you can make adjustments. So then notice that in the problem here, we've got derivatives. So that suggests that we're going to take a derivative on this. And so we have to think about differentiating something to the -1 power. And so you will get negative that thing to the -2 power, but you're taking a derivative with respect to t. So the chain rule says you got to have that on there. And then something that's very close to the same thing appears in all the other terms. I have to be honest in saying that I am not a fan of using subscripts, but textbooks use them all the time, so I'm kind of going with the flow there, right? Now, once you've implicitly differentiated, plug in everything you know, right? That is often a key thing that's going on in these problems, or any math problems, is once you get an equation with a bunch of stuff you don't know, plug in the things you do know. So here, for instance, the minus 46.154 squared dr dt is there. And then over here, the minus R1 was 75, and dr dt, or dr1 dt, was 0.8 ohms per second. And then minus 120 squared, and dr dt was minus 0.4 ohms per second. So the dr dt that we're looking for, we can go ahead and do this together here. With the 46.154 squared. Now, I left that 46.154 squared on the calculator. So that means that I'm gonna, I forgot my minus. I'm going to be able to go ahead and put that stuff together relatively nicely. So 75 times 0.8 And 120, folks, I almost messed up pretty good there. I forgot to copy my squared down there. Oh no, it's worse than that. It's the negative 2 power, isn't it? Man, copying errors can really goof stuff up. Okay, so now I have to say negative of 75, and so 75 to the power of negative 2, then times 0.8, and then the 120 to the power of negative 2 times 0.4, close, divide, answer squared. All right, I am getting an answer here that I don't really like of 5.373 e minus 8. Yeah. Right. So you might check my arithmetic on that because sometimes I type things in the calculator wrong. So, all right, let's take a look at another one here. Just a couple more, and we're going to have to call it an end on this. But I wanted to try to give you all enough examples to get you started and stuff. So we've got a spotlight that is 0.5 meters from the ground. Most problems like this just put the spotlight on the ground, and I wanted to make one that was a little bit different, just to make it seem a little more realistic. Maybe not a lot. The spotlight, 0.5 meters from the ground, shines on a person who is 1.6 meters tall, and they walk towards a wall that is 20 meters from the light, and they're walking at 2.1 meters per second. So keep in mind with that, since they're walking towards the wall, then the thing that I labeled as X is getting smaller, okay? So that means we have got a negative value for dx dt. All right, so the trick on this one is that we're thinking about similar triangles. And with similar triangles, man, oh, that's not very triangular. With similar triangles, the main thing about them is that when you cut something parallel to one base, then the smaller triangle you get is going to be proportional to the bigger triangle, okay? So we're going to be able to make some relationships here. And one that was purposely hidden a little bit is that we have 1.1 meters there. That 0.5 meters that the spotlight went up from the ground cut off just a little bit, okay? So then we're going to be thinking about the part we've got here. The h minus 0.5 is a base of a large triangle, and the 1.1 is a base of a small triangle. And the 20 minus x is a side of is a side of a small triangle, and then going out here a ways, the 20 is going to turn out to be the side of the big triangle. Okay, so our similar triangle says that 20 minus x over 1.1, so basically the tangent of this angle here, maybe the cotangent of that angle there, either way you want to think about it, but that needs to be equal to the 20 for the big triangle divided by the h minus 0.5. Okay, so you could either leave things like that, or you can cross multiply and have 20 minus x times h minus 0.5 is equal to 22. Okay. So once you have that notion in hand, I'm going to take and move those over here from the diagram, or away from the original diagram. And maybe I'll move this down a little bit here. It's probably handy to say 20h minus xh and plus 0.5x, and I lost my place, minus 10. Yeah, that all that needs to be equal to the 22. Heck, I think I will take and add the 10 to the other side, say that is equal to the 32. All right. Now we've got something that we can implicitly differentiate, and we can fill in the things that we know after we've done that. So going down through here, we'll have 20 times dh dt. Keep in mind, dh dt is what we actually want to know. What rate is the shadow shrinking at? Minus, now the x times h, we're going to have to do a product rule and have dx dt times h plus x times dh dt. Okay, and then plus 0.5 dx dt, and that all is equal to 0. Okay, now we have values for some of these, but not all of them, right? So 20 dh dt minus, he is walking towards the wall, so that meant negative 2.1 h plus he is how far from the wall? 8 meters dh dt, and then plus 0.5, and the dx dt we said was negative 2.1. Okay, so a little bit messy. We don't have a value for h. We can get it though, can't we? Because if you come back over here to this expression here, or maybe this expression there, that's probably the easier way to do it. We can go ahead and fill in and have 20h minus x is 8, h plus 0.5, the x was 8, equals 32, which says 12h is equal to 28. H is equal to 28 over 12, which is 7/3. Okay. Pardon me. So we've got a number for that, and let's go ahead and fill that in. All right. So I'll have 20 dh dt and minus 8 dh dt plus 2.1 times 7/3. Gosh, what is that? 2.1 times 7/3 is 4.9, and then minus 0.5, 0.5 times the 2.1 is 1.05. And so you end up with 12 dh dt. Weird that the 12 showed up in two different places, is equal to negative 3.85, which says that dh dt is going to be equal to negative 3.85 over 12 divided by 12. So negative 0.325 0.08. So I'm going to write it as 0.321, and that is in meters per second. All right. Hopefully that feels all right. Let's take a look at just this one more problem here. All right. So this one, the relative rate of change of a function f is given by df dt divided by f. So after we have the function's derivative, then we're going to divide by the function itself. Okay. A labor union claims that the rate of increase for wages should have the same relative rate of change of the revenue for the company. So for a company with a revenue function given by this, I am not an economist. I don't know. That doesn't seem like a realistic thing that somebody's actually studying, but maybe it is. Anyway, a company has a revenue function given by that and an average wage of $25 per hour. What is the proportion between the relative increase in revenues and wages? Okay. So the essential thing we're going to do is to calculate this df dt, but it's for r. So it's going to be dr dt and divided by r, of course. So we'll just go ahead and write down dr dt, and we've got to go to that equation there, and there's a 0.2 times, now the derivative of L cubed is 3L squared, but then we have to write dl dt, okay? And then minus 4 times 2L dl dt, okay? So that is going to be 0.6 L squared and minus 4.2 L dl dt, okay? And so from that, we're going to then go ahead and calculate the dr dt divided by the r. Maybe I should have written that to slant a little bit better because I'm going to have space concerns here in a minute. Dr dt divided by r. So the 0.6 L squared minus 4.2 L dl dt divided by the 0.2 L cubed minus 0.4, not 0.4, just 4, sorry, 4L squared. Now, you might be kind of wondering here, we don't have everything, right? We don't have the value for dl dt, but this is talking about a proportion between the relative increase in revenues and the relative increase in wages. So what we're going to do here is to spot that you can factor an L out of the denominator and have this 0.6 L squared minus 4.2 L. That like so. Actually, you can do a little bit more than that. Okay, sorry folks, I am gonna try to make this nicer. So you can take an L out of the top and have a 0.6 L minus 4.2 left, okay? Out of the bottom, if you notice, you can take an L from that and another L, which I'm going to mysteriously just leave separate for a moment, and have 0.2 L minus 4. So basically, I just factored out an L squared there. The reason that that is mysterious is that I've got this dl dt here, and I'm going to take and grab this L and move it over there, okay? So the relative rate of change of the function R is given over here and the relative rate of change of the function L is given over here. And so this is the proportion between them. That's the thing that's actually asking for in the question. So I'm going to take that right there, copy it, and put a copy of it right here, and then I'm going to put in here that we're going to evaluate it when L is equal to 25 and see what we actually get there. And so I've got to say 25, oh, this is untidy. So 25 times 0.6 times 25 minus 4.2, all that divided by, you know what? I needed to have spotted here that I could cancel those so that when I did this calculation here, it would be so much nicer. All right. So then down here, I have a 0.2 times the 25 minus 4. So let's see, what is that? 15 minus 4.2, then divided by 5 minus 4. So 11, 10.8. You might want to check me on that. But the proportion between the rate of change of the revenue increase and the rate of change, relative rate of change of the revenue increase and relative rate of change of the labor increase is 10 times, nearly 11 times. And what that's saying, should be no surprise to anybody who's done actual business stuff, is that revenues are increasing much faster than the labor costs are increasing. So happens a lot. I have no idea whether folks who are doing actual economics sort of stuff of fairness and stuff, whether that's an actual argument that they make. But it makes calculus be somewhat relevant. So, all right. Anyway, that should get you enough. You're probably tired of listening to me. I'll see you all in class.